Last time we talked about the multi-random variables, which means here we only think about two random variables. So for two random variables, then we have our joint CDF and also joint PDF or PMF. And we need to know how do you find the joint CDF? Here's the definition. And then for the joint PDF or joint PMF, here is also the definitions, and you can see how to find that. And we also talk about the properties of the joint PDF and the joint PMF. Today, we will continue and finish this part, and we will go to the conditional random variable. Before that, let's learn what statistical independent random variable is. Okay, so for the statistically independent random variable, this random variable means that if two random variables x and y are independent, then what does that mean? Their joint PMF or joint PDF will be the multiple of their individual PMF. For continuous case, the joint PDF will be the multiple of your individual PDF. So here, let's recall, I have two events. They are independent. If two events are independent, that means your probability of your intersection will be the multiple of your probability, individual probability. Okay, so now for this event A, we can let the event A as the random variable x equals some value x, and also event B will be the random variable y that equals some value y. So now let's see this A and B, the intersection of A and B. The probability of x equals certain x intersect the random variable y equals y. Then if they are independent, then it is the probability of your x equals some x and your random variable y equals some value y. And what is the probability of your random variable x equals some value x? That's the PMF. And then for probability, your random variable y equals some value y, that is your PMF of y. So this is precisely the relationship of your joint PMF. If they are independent, that be equal to the multiplication of each PMF. That is for the discrete case. We can also let this event is the random variable x less than or equal to some value x, and the event B is the random variable y less than or equal to y. then the probability X, the A intersect B. Because they are independent, these two events are independent, so there will be probability of your X less than or equal to X, and your probability random variable Y less than or equal to some value Y. Now first, what is the probability of your random variable less than or equal to some value? That is your CDF. And then here it is also CDF. So in this case, we have fxy with joint CDF. That will be the multiplication of their individual CDF. From here to here. Then to get your PDF, your joint PDF, we can take the derivation. So furthermore, the joint PDF, you take the partial derivative of your joint CDF. And here we know that since they are independent, so I have the CDF over X and then times CDF over Y. So we get PDF of X times PDF of Y. So for this definition, we will know that if we say that two random variables are independent, then what should you pop up from your mind? You join PDF or join CDF, join PMF or join PDF. They can be written as the multiplication of your each PMF or each PDF, or your CDF similarly are exactly the same. Your joint CDF will be the multiplication of each individual CDF. Now we know that this is the definition of your independence, or we say statistically independent. This statistically just compared to linearly independent. They are a little bit different. So we call here independent, statistically independent. And then we will learn what is the IID, the independent and also identical distributed. We say a collection of random variables from x1 to xn are independent and also identical distributed, or we say IID, if they follow these two requirements. First, x1 to xn, they are independent. And x1 to xn, all the these random variables have the same distribution. Have the same distribution means the PDF of x1 is equal to the PDF of x2, and so on. So they have the same distribution. All the PDFs are the same. So since all the PDF are the same, then their ID, their joined PDF, because they are the same, so there will be the multiplication. Well, the joined PDF will be the multiplication of each PDF. And since the PDF are the same, so we can just choose one, and we have n times of this distribution, the PDF. So there will be this PDF to the n power. And then for the particular choice of F1, I think we can also put here like F1. It doesn't matter because the PDFs are the same. F1 or X1, the PDF of X1 will be equal to PDF of X2 till PDF of Xn. All right, so now we can talk about their expectation. We learned the joint CDF, joint PDF, joint PMF, and know the independent. How do we? What's the properties or definition of your independence? Then, what are the joint expectation? We say two random variables x and y. Their joint expectation. This is for the discrete case. And the second one is for the continuous case. Expectation, I always consider all possible outcomes. So here, possible outcomes, we have the x and y. All possible outcomes times their weightings. The weightings is the joint PMF. That is for the discrete case. For the continuous case, I consider all. So here is consider all possible outcomes x, y. And then their corresponding weightings, joint PDF. For joint expectation, we also call it the correlation. Okay. So joint expectation, sometimes you may see that what are their correlations. That means they need to find the joint expectation. And then for the correlation, we also write this symbol core xy, and it is defined for expectation xy. And if x and y are independent, how about the joint expectation? How can we express the joint expectation? Since here we know that this is we will prove that from here. So let me give you the result first. The joint expectation or the correlation will be the multiple of their individual expectation. Here, let's see, from the definition of your joint expectation, consider all possible outcomes times the weighting, their corresponding weighting. Their corresponding weightings is the joint PDF. So since they are independent, we just done that if they are independent, their joint PDF will be the multiplication of the individual PDF, fx and also fy. So we can separate the x and y. We have the x times f of x dx, and then integration for y. Now, from last session, we just mentioned that we always know the definition of the expectation. And now, how about looking in the opposite way? If I have this integration, what does that mean? I have x times f of x. Oh, then let's see, consider all possible outcomes times their weightings. So this is the expectation of x, and the other one is the expectation of y. So we can see that if two random variables are independent, then we can also see that their joint expectation, or the correlation, will be the multiplication of their individual expectation. Next is the joint moment and the covariance. So what is joint moment? If I have two random variables, x and y, the joint moment is I have x to the kth power and y to the lth power. And for discrete case, here's a discrete case. And the bottom one is continuous case. The joint moment, you can also think about the function of your random variables. Well, so consider all possible function of outcomes. So always consider all, and whatever you have in the expectation, this notation, you copy it times the corresponding weightings. That is the joint moment. And then covariance. The covariance, the definition here is similar to variance, but here we have two random variables. So we will see the difference of your x and the random variable x and their mean times the random variable y minus their mean. That is the covariance. Based on this covariance, the definition of covariance, here are some notes. The covariance, we can also write it down as your correlation minus the multiplication of your expectation, because the covariance is the expectation. You know the difference of your random variables and your mean. So let's take the parameters out. Then I have an xy minus x mu x minus y mu y mu x mu y. Remember that what is the mean, the mu x and mu y? They are constant. So there will be like a constant x. I can take the constant outside. So those are the constants, or I can use this. They are constants. So I'll get the correlation minus mu x times mu y. So here you can see that if your random variable y equals x, if y equals x, then your covariance becomes the covariance x and x. So replace y to x, then we have expectation of x squared, the second moment minus the first moment squared. So if your y equals x, then your covariance is just the variance. And the next property for the covariance, if two random variables x and y are independent, then their covariance is 0. Because we know the covariance of x and y that's the correlation minus the multiplication of the mean of each random variable. If they are independent, the correlation becomes the multiplication of each mean or each expectation of your random variable. So that's why they are 0. So here we see if they're independent, two random variables are independent, then we can imply the covariance is 0. If covariance is 0, can we imply x and y are independent? Actually, that you cannot apply that they are independent. This is only one way. If two random variables are independent, we can imply that their covariance is 0. But covariance is 0 doesn't mean that x or y should be independent. So here, let's see the example, the counterexample. So suppose I have a PMF of z that is 1/4, and your z is 0, 1, 2, 3. And then now that the x is a cosine pi over 2 times the random variable z, and y is sine pi over 2 times the random variable z. What is the expectation of x and what is the expectation of y? Because if you want to find the covariance, then we need the correlation and also their individual expectation. So first, let's just find their individual expectation. For x, that is cosine pi over 2 times z. So consider all possible function of outcomes, k from 0 to 3, because z is 0, 1, 2, 3. Cosine pi over 2 times k, and times their corresponding weighting, which is 1/4. This gives you 0. Similarly, for the expectation of y, is a sine function. Again, that to sum a circle, then their summation is also 0. Then let's see the covariance. The covariance will be your random variable x minus the mean. Now we know the mean is 0, and the covariance, the random variable y minus the mean. The mean is still 0. This is the expectation of xy. And then now here let's find this correlation. That is the expectation cosine pi over 2 times z times sine pi over 2 times z. This is 1/2 of your sine pi z. This is the summation k from 0 to 3, and 1/2 of sine pi k times 1/4 the weighting. So this is still 0. So their covariance is 0. But now we need to check x and y if they are independent or not, even though the covariance is 0. So, and apparently it is not in this case. So we need to show that the joint PMF is not equal to the multiplication of their individual PMF. Okay, so now let's see this. To find the joint PMF, how do we find the joint PMF? For z could be 0, 1, 2, 3. So when z is 1 and z is 0, what does that mean? Z equals 0. When z equals 0, cosine 0 is 1, sine 0 is 0. That means your x is 1. And your y is 0. When z equals 1, I have cosine pi over 2 and sine pi over 2. So the x is 0 and y is 1. When z equals 2, x is minus 1 and y is 0. And when z equals 3, we have x equals 0 and y equals minus 1. So now we have this combination. 1, 0, 0, 1, minus 0, minus 1, 0, and 0, minus 1. Let's see their PMF, joint PMF. So I only have this combination. So when x and y are 0, then their joint PMF is 0. And when x is 0, x is 1, y is 0, then that means z is 0. When z is 0, the PMF is 1/4. Similarly, for x equals minus 1 and y equals 0, this is 1/4. So I can give you like 1 minute, then you can try to fill out the rest of these numbers in this table. Okay, what is the PMF, joint PMF of 0 and 1? and 0 and also minus 1. What are they? So here you should have 1/4, 1/4. Here we don't have this combination, so there'll be zeros. Zeros. That is your joint PMF. And then I also need to find the marginal PMF. For the marginal PMF, because we need to find if this joint PMF is equal to the multiplication of their marginal PMF. So here, what is the marginal PMF of X? That means I don't need Y, so I need to sum the Y out. So if I sum the Y out, then first we can see when X equals 0, then we need to sum Y, P of XY, and your Y is 0 and Y. For this, when X is 0, this is X is 0, so actually I'm doing the summation of this part. This is the PMF of X at 0. So here you get 1/2. And how about X equals 1? So X is 1 and Y. So here is X equals 1. So here we get 1/4. And how about X equals minus 1? This part. Okay, similarly for the marginal PMF of Y. To find the marginal PMF of Y, we don't need X, so we need to sum the X out, so do the summation with respect to X. So first, we will see the Y equals 0. That means the PMF, the joint PMF of X and 0. In this case, Y equals 0. That will be the first row. This is the PMF of Y at 0. So when you do the summation, you will see that this is 1/2. And then for Y equals 1, that'll be the second row. Okay, so this is your marginal PMF at Y equals 1. Then you'll get 1/4. Then the last one, you can expect when y equals not to minus 1, I'll get the third row. For the third row, this is the marginal PMF of y equals minus 1. Then you'll get still 1/4. So apparently, your joint PMF is not equal to the multiplication of their individual marginal PMF. So we know that the joint PMF is not equal to the multiplication of their marginal PMF. Although their correlation or the joint expectation is the multiplication of each expectation so only one way. If they are independent, we know the covariance is 0. But if the covariance is 0, it doesn't imply that two random variables are independent. The next part is for the covariance. Okay, we just know that if they are independent, then the covariance is 0. The other way around, that is not correct. So overall, for two random variables, they are not necessarily independent. If they are not necessarily independent, let's see some properties. X and y. So the expectation of x plus y, it is like a linearity. Okay, so there will be the summation of your expectation of x and expectation of y. Quickly prove this. We know from the definition. Okay, so here let's see the definition. For the discrete case, what is the expectation, the joint expectation? That is to consider all possible outcomes, x plus y, times their corresponding weightings. That's the joint PMF. Okay, we can separate these two parts, the x times the joint PMF and y times the joint PMF. So here we have the summation for x times the joint PMF, and then the y times the joint PMF. So for the first term, let's rewrite it. I can separate the x and y. For summation of x, I have x. And then for summation of y, we have the joint PMF of xy. For the second term, similarly, I take the y outside and doing the summation of x. Let's see this part, the summation of y for the PMF, the joint PMF. This you can think about that I'm going to sum y out, then I will get the PMF of x. So this is our marginal PMF of x. Similarly, here we have the marginal PMF of y. Then x times your PMF of x. And doing the summation, what is this? Consider all possible outcomes times their corresponding weightings. So here we have the expectation of x. And then the second term will be expectation of y. The next one, the variance of x plus y. There will be the variance of x plus variance of y, and I have 2 times the covariance. So again, for the variance of x plus y, by the definition, that is the expectation of x plus y squared minus the second moment minus the first moment, so square. This we have x squared plus 2xy plus y squared minus the mean squared. Then there's x squared. Let's rewrite it. So x squared, the expectation of the second moment, minus the mean squared. And also the second moment of y minus the first moment squared. And then we have the rest part. The first part is the variance of x, and second part is the variance of y. And the third, we just know that this is a covariance. So it's covariance xy, and 2 times of the covariance. So if x and y are independent, the covariance is 0, then our variance of x plus y just becomes the sum of their variance. Next, we are going to talk about the correlation coefficients. Okay, what is the correlation coefficients? This coefficient is defined as the covariance divided by the square root of the multiplication of each variance. So when x equals y, these 2 random variables, they are the same, then this correlation coefficient, though, will become positive 1. and we say this is a fully correlated. And when x is minus y, then the correlation coefficient is minus 1. It is negatively correlated. If x and y are independent, there is no correlation coefficient. The coefficient is 0. Well, again, then, if they're independent, the correlation coefficient is 0. If the correlation coefficient is 0, does that imply that x and y are independent? Here, also, no. And you can see the correlation coefficient is always between minus 1 and 1. They just need to know the relationship between the x and y. How correlated of the random variables x and y. And why it is from minus 1 to 1. That's proof that first, using the Cauchy inequality, we know that xy square a square ab square will be less than a squared times b squared. That is the Cauchy inequality. Therefore, let's see the covariance. The covariance xy squared. This covariance is expectation x minus the mean times the random variable y minus its mean squared. You can think about this as ax, this is y. So applying the Cauchy inequality, this is less than or equal to the random variable x minus the mean square times the expectation random variable y minus its mean square. And here, this is the variance of x times variance of y. So this is less than or equal to variance x times the variance of y. And then that's just divided by the square root, well, divided by the variance of x and variance of y. And then take the square root. Then we have covariance xy divided by square root of variance of x times variance of y. That's between minus 1 and 1. Okay, so now let's see an example. Let's see 3 examples. The first one, the joint PDF. Here's the joint PDF. Now I need to find the constant C. Remember that if I say that this is the joint PDF, then they should satisfy the property of the joint PDF. So to be a valid joint PDF, first we should know If I do the integration of the joint PDF dx dy, this integration should be 1. Okay, to make sure that this joint PDF is a valid PDF, then we need to satisfy this property. So in this case, let's see, my x and y are from 0 to 1. See x e to the minus y dx dy. This should be 1. So your constant c is 2e over e minus 1. For next example, I have the joint PDF, then I still need to find the c. And then I need to find the probability. Okay, so first let's find the c. To find the c, because this is the PDF, joint PDF, and then to integrate this joint PDF, it should be 1. U, that's unit step function, so we have this value is 1 when x is greater than 0. So in this case, we can get your c is 2. Now, how do you find this probability? I need the probability of your x is greater than 1, and also intersect y is less than 1. X is greater than 1, so it should be from 1 to infinity. And y is less than 1, so it should be from 0 to 1. C is 2, so 2 times e to the minus x, e to the minus 2y, dy, dx. That is, we take the integration of y first. So I have the x is from 1 to infinity, e to the minus x. And the e to the minus 2y, into the integration, that will be minus 1 over 2 times e to the minus 2y, y from 0 to y equals 1. So here you have 2 times minus 1 over 2 e to the minus 2 plus 1/2. And then now let's do the integration for x. So the answer is minus e to the minus 1 minus e to the minus 3. Okay, the last one. If I have a joint PDF, how do I find the marginal PDF, x? Okay, to find the marginal PDF, we have f over x. How do I find the marginal PDF? That means I want to find the marginal PDF of x. That means I don't want the y, this factor. So I don't need the random variable of y. So I need to take the random variable y out. So here I have a joint PDF, but I take the integration with respect to y. So for y, that's from 0 to 2, xy dy. That gives you 2x. And then this is not the final answer. You still need to tell that fx is 2x, and how about the range of x? The range of x is still from 0 to 1. Okay, so for next, we're going to talk about the conditional random variable. Let's see, so far we just done the random variable, a function of random variable, and two random variables. And then the next is the conditional random variable. To learn the conditional random variable, you will expect to know that how do you find the conditional CDF, conditional PDF, and then their expectation. How do we find those? Conditional expectation. So first, let's see. The conditional random variable. We have a random variable x and two events A and M in the event space. So the probability of A condition on M. This, we just learned that in the first class. That's the probability of A intersect M divided by the probability of M. And we assume that M, the probability of M should be greater than 0. So now A and M are two events. Let's just let by A, this event is the random variable x less than or equal to some value x. Some value x means that there's a C in the sample space such that if I map to the real line, this is less than or equal to some value. Okay. So in this case, what is the probability of x less than or equal to some value conditioned on the event M? So you can think about if we don't have this part, what is the probability of your random variable less than or equal to some value? CDF, right? This is like CDF. Now a condition on M, you can think about this as also a CDF. But this CDF is your x conditioned on M. So now we can define the conditional CDF of x conditioned on an event M. So this is it should be capital F because this is CDF. Okay, the CDF of x conditioned on M. That is define the probability random variable x less than or equal to some value M x conditioned on the event M. So in this case, I have the probability your event x is less than or equal to some value intersect the event M divided by the probability of the event M. What is the random variable x less than or equal to x? That means I have an outcome in the sample space such that when I map this outcome to the real line, this number is less than or equal to x, some value x. So here's a note. The definition of this conditional CDF is just like the definition of your CDF. But now I just changed the probability to probability of the conditional probability depending on the event M. So this is a valid probability measure. Then your conditional CDF is a valid CDF. So this conditional CDF contains all the properties that we have learned. So if I have a probability, if I want to find the probability of my x is between A and B, and that is conditioned on the event M. That will be the conditional CDF of B conditioned on M minus the conditional CDF of A conditioned on M. Okay, and then this is the conditional CDF. Then you can also expect, if I take the derivative of this conditional CDF, I should get the conditional PDF. So here, the conditional PDF of x conditioned on M in the event space, this M. Okay, then here is the formula. I take the derivative of the conditional CDF with respect to x. And since the conditional CDF is a valid CDF, then the conditional PDF is also a valid PDF. PDF. So the probability of your random variable x between A and B conditioned on M, I can also write it down this as doing the integration from A to B of your conditional PDF. So here the event M, we just condition on an arbitrary event M. And this M, of course, is in the event space. And sometimes for this event space, this M, I can also describe this M in terms of the random variable x. Okay, for example, like this M is that the random variable x is less than A, or the random variable x is between A and B. Then how do we find their conditional CDF and even the conditional PDF? So, for example, if this event M is here, the random variable x is less than or equal to a value A. Let's find the conditional CDF. So for the conditional CDF, we know that is the probability of your x less than or equal to x, some value x, conditioned on another random variable, no, the random variable x less than or equal to a value A, some value A. Okay, so this is the probability of your x is less than or equal to x intersect x is less than or equal to A divided by the probability of x is less than or equal to A. In the denominator, we know that what is this? Probability of x less than or equal to some value a CDF. And how about the numerator? Numerator, we need to compare these two values, x and A. So if x is greater than A, then what is the intersection? The intersection, x less than or equal to some value x, intersect the random variable x is less than or equal to some value A, they will become x is less than or equal to A. Therefore, your conditional CDF will be probability of x less than or equal to a divided by probability of x is less than or equal to a. So this is the CDF of x at a divided by CDF of x at a, then gives you 1. Okay, this is the first case. How about x is less than a? So for x is less than a, their intersection becomes the random variable x is less than or equal to that certain value x. Therefore, the conditional CDF of x given m is the probability of x less than or equal to x divided by the probability of x less than or equal to a. So the numerator, that will be the CDF of x, and the denominator is also the CDF of x at a. Therefore, we can combine these two conditions. Then our conditional CDF is either the CDF of x divided by the CDF of x at a when the x is less than or equal to a, or it is 1 when x is greater than a. And we can also plot the CDF. So here is 1, and also a. This is 1. Here's a. Now my conditional CDF should be this case, f of x condition on x is less than or equal to a. And you can see that the CDF of x actually, well, this should be our CDF of x. To find the PDF, conditional PDF, take the derivative. Okay, and when you take the derivative of this part, you get the PDF of x divide the PDF of x divide by a c. Well, here. If I take the derivative of this part, you know that actually this is a constant, and then this is just the function of x. So here I have the CDF of x at a when x is less than or equal to a, and here I have 0 when x is greater than a. And we can also plot This is X, and here's Y. And this is A. So the PDF, the conditional PDF is like this. And then after A, it becomes 0. This is our conditional PDF. And my conditional PDF, or no, just the PDF. That is the case 1. When my event X, event M, that is the random variable X less than or equal to A. The next will be this event A is the random variable X is between A and B. Now let's see the second case. Okay, the second case, my event M is the random variable X between A and B. So between A and B, and we know that A is less than B. So the conditional CDF in this case is the probability of your random variable X less than or equal to some value X intersect the random variable X between A and B. Divided by the probability of your M here. So in this case, we have 3 distinct deterministic values, X, A, and B. So we have to think about it in 3 cases. Okay. So first is the X is greater than B. And then the second one, X is between A and B. And the last one, X is less than A. So in this case, if X is greater than B, then what is the intersection? For example, this is like 1, 3, and here is 5. Okay, X is less than 5, and X is also between 1 and 3. Well, first I think I should. Well, suppose first X is less than A, less than or equal to A. So here is like a 3, here's a 4, 5. There's no intersection. So I got empty set. When X is less than or equal to A. When X is between A and B, so suppose this is 4, and A is 3, and B is 5, then my random variable X should be between A and X. So in this case, X is between A. If X is greater than B, 5, and this is 3, 4, then my X is between A and B. Then our CDF, based on this part, so can bring this part to the numerator. So we have The first case, when x is less than a or equal to a, and my CDF is 0 because it's an empty set. So x is less than a. If x is between a and b, then my CDF is the CDF of x minus the CDF of x at a. And the numerator is always the CDF of b minus the CDF of x at a. That is when x is between a and b. In the third case, will be f of x at b minus f of x at a divided by the same thing, x as x of x at b minus f of x at a. That is 1 when x is greater than b. So if I take the derivative of my conditional CDF, I'll get the PDF, the conditional PDF. So when I take the derivative, it's still 0. When I take the derivative, this one is still 0, right? Because they are constant. I only have values when x is between a and b. Remember, this is a constant. So when I take the derivative, I only have this part. So the conditional CPDF f over x condition on the random variable x between a and b. That is taking the derivative of your CDF, conditional CDF. That will be the PDF of x divided by the constant. Instead of using, well, here we can use the indicator function. So x is between a and b. And we can plot the PDF. For the PDF, conditional PDF, here a and b, then I have 0 outside the region of a and b. This is our conditional PDF. And my PDF over x will be like that. And we can also plot the CDF. Here's the CDF. As still have A and B. So before A, the CDF is 0. And B, there'll be 1. And my CF of X could be okay. Now let's see. The next we are going to talk about the probability law, the probability law and the Bayes theory. Okay, because now we just done the conditional random variables. So we can use this concept to talk about the probability law and the Bayes theory. So I have a random variable X, and the event A1 to AN are the partition of the sample space, or in S. Then what is the probability of your random variable X less than or equal to some value X? We can think about this probability as your probability, your event conditioned on A1 times the probability of A1. And then also this event conditioned on A2 times the probability of A2. And we add all this together because the partition, this is A1, A2, A3, A4, A5, till AN. Okay, so the probability that random variable X less than X, I take part of that and also part of this, and then summation them to sum of them. So we know actually probability of X less than or equal to some value, that is the CDF of X. And then this expression is the conditional CDF of X, conditional on AK. So in this case, we can write it down. We can substitute this probability part. Then we have the CDF of X actually is the CDF of X conditioned on A1 times the probability of A1 plus the conditional CDF of X conditioned on A2 times the probability of A2. And we're doing the same thing. The last term will be the conditional CDF of X and conditioned on AN times the probability of AN. Then we can take the derivatives with respect to X on both sides. Then we get the PDF of X. So for the PDF of X, here is the conditional PDF of X, condition on A1 times the corresponding probability of A1. And then the conditional PDF of X, condition on A2 times their probability of A2. And the last term is the conditional PDF of X conditioned on AN times the probability of AN. Now let's recall the Bayes formula. Okay, the conditional PDF probability of A conditional on B, that is equal to the probability of B conditional on A times probability A divided by the probability of B. So if we let the B event is related to the random variable x less than or equal to some value x, and now also x1, Now, in this case, this conditional PDF is the probability of your x less than or equal to some value x, condition on A event times probability of A, and then divided by probability of B. Now we know that the B is x less than or equal to x, so here we can change that. So this is the random variable x less than or equal to some value x. So that is the probability. Okay, then we can put it here. So here you can see that in the numerator, the first part, that is the CDF of x, because if you don't see this, this is the CDF condition on A. So here is the CDF of x, condition on A times the probability of A, divided by the CDF of x. Now how about the event B? The x, random variable x is between x1 and x2. And x1 is less than x2. So this probability, conditional probability, that will be the probability of the random variable x is between x1 and x2. Condition on A times probability of A divided by the event B, which is the probability of x between x1 and x2. That is the CDF, conditional CDF over x at x2, condition on A, minus the CDF of the conditional CDF of x at x1, conditioned on A, and then overall times the probability of A, divided by the CDF over x at x2, condition on A, minus the CDF over x at x1, condition on A. Now we just consider that the B, here the B is either random variable x less than some value, or the random variable x is between two values. And how about the random variable x is equal to a certain value? And what is this probability? So we can let my B, this event B, as an event that the random variable x is equal to some certain value x. Then we will try to use the similar trick to find the conditional probability. And here we can see that the probability of A intersect another event x equals a certain x, and the probability of this random variable x equal to certain x. For the continuous case, we know that this probability is 0. Here, this is probability is 0, and this is undefined. Oh, a reason is if the x is continuous, the continuous random variable then the probability of x equals some value that's 0. And also event A intersect x equals some value x that is inside the x is equal to the x. So the probability of A intersect x equals x, that's 0. Then we need to fix it because mathematically this is undefined, but in reality sometimes this is practical. In some cases we need to condition some events that my random variable x is just equal to a certain value. In this case, we can think of the second case, x is between two values, and these two values right now is x and x plus delta x, a small x increase. And then we can consider the limit to let the delta x goes to 0. Then if this works, then we can define the probability of event A condition on the random variable x equal to a certain value. If I take the limit, here I need the, maybe this is a star equation. Then based on the star equation, okay, we can rewrite that. Okay, I have so many limited space. Wow. This is from the star equation. When we take the limit and let x go to 0, we'll have the CDF over x plus delta x condition on A minus the CDF over x condition on A divided by the CDF over x plus delta x minus the CDF over x, and overall times the probability of A. Okay, let's divide by delta x. Both sides. So limit delta x goes to 0, and the CDF of x plus delta x condition on A minus the CDF over x condition on A, and I divide by delta x. So in the denominator, I also divide by x to make it balanced. So here I divide by x, delta x, And we have the CDF over x plus delta x minus the CDF over x. And overall times the probability of A. And here we can get the PDF over x conditional A, the conditional PDF, divided by the PDF of x times the probability of A. Then we have the formula. The probability of A conditional on x equal a certain value. Then here, the conditional PDF, conditional A divided by the PDF, time overall times the probability of A. From this equation, we can multiply f of x on both sides, or you take the f of x to the left-hand side. Then we have f of x. Maybe you put here f of x conditional A time equals no, I also need to times the probability of A. That be equals the conditional probability A conditional x times the PDF of x. And then I can do the integration. When I do the integration, probability A, this is nothing related to the x, so I can put it outside. So when I put it outside, then I have a probability of x given A dx. And then the right hand side, I still have just the same. So what is this part? The integration. For your PDF, you should be alerted that every time when you see the PDF, you take the integration. Think about the property of the PDF. If you integrate, find all the areas above this, because this is the PDF. When you take the integration, there will be the probability. And if you consider all areas under your function, then it should be 1, because the probability, you consider all this, and then this probability should be 1. So here the integration is 1. Then you get another way to find your probability of event A. That is, the integration, consider each part that A conditional x times the PDF of x. This is the total probability law. We can also rewrite this equation 1 to express the conditional PDF f of x conditional on A. If I consider the PDF of x conditional on A, that is the probability of A condition on x equals x, and f of x divided by probability of A. Now we just learned we can use the total probability law to express probability of A. So let's print this in here. So according to the equation 2, same as the numerator. So we just copy it and rewrite it. And in the denominator, the probability A will be the integration this is the base theory. Okay, so far we just learned the conditional random variables with their PDF and CDF. If I have two random variables, then how do I express the conditional CDF or PDF of them? So here we have the conditional PMF of two random variables. I have two discrete random variables x and y. Then what is the conditional PMF of x given y? Because here we just have like one random variable condition on the event A. Okay, and then the event A. Now we can think about now this event A could be related to another random variable y. So the conditional PMF of x given y will be their joint PMF divided by their marginal PMF of y. So you can also define the conditional PMF of x given y is equal to the probability, because we know the PMF is the probability. So for the PMF of x, that means the probability of x equals k. So here that means my x is equal to some value x, but given the random variable y equals some value y. Here let's see why, because what is the PMF of x given y? That is the joint PMF divided by the marginal PMF of y. The joint PMF means the probability of your x intersect the y. And then divide by probability of the PMF of y is the probability of random variable y equals y. And then this is just the probability of x equals some value x given the y is equal to y. So here you should know there's a very important note that the random variable y is fixed to a specific value. Okay, so it is fixed, it's not random. So there is no randomness associated with the random variable y. And then the variable x in this conditional PMF, they'll describe the randomness. So only x describes the randomness. Y is fixed. You can think about that y is 5. Okay, y is all fixed. So if you do the summation, if you take the summation of x prom for this PMF, then according to the definition here, we can simplify it. Since this is the PMF of y, nothing related to x, so I can put the summation on the numerator. So here, I have the summation x prom p x y x prom y, and then the PMF of y. What is this part? The join the PMF and then take the x and sum x out. Then this one I get the marginal PMF of y. So this becomes 1. But if you do the same thing, but you take the summation with respect to y, what happens to this? Again, like we can write it down. This is y prom. And here we have the joint PMF of xy. And then the PMF of y. And you can see that I cannot, because I have a y prom and y prom here, this cannot be equal to 1. So the conditional PMF of x given y, this is the probability of the x. Okay, not the probability of y. But the conditional PMF can be a function of both x and y. But the x given y, that just means that having the random variable x random variable x equals x given that y is fixed. The random variable y is fixed, is at a fixed value. Y.